a change of stage. If you're into a new stage in your algorithm, a new component or part, that's typically when you'll change the state. And a stage may have substages, and they may have substages, and so on. And you may be changing state a lot. You may have many states. All right. Okay. So we mark the first node, and then we go into stage 2, and then you're looking to find an undotted node. Okay. Call that undotted. You call that undotted node N1, right? And you mark it somehow, but using a different marker. So it probably wouldn't be dot. It might be underlined. So it'd have a new character. The node number underlined, let's say. So you're pinpointing it. Okay, so for example, by underlining the first symbol. All right, now you go into a sort of a subloop. So 2 is calling on these steps 3 multiple times. Okay, so you found an undotted node, and its node number is N1, let's say, right? Now then you scan the list again. To find a dotted node. Oh, I see. Okay, maybe not the most efficient way. So you scan the list again. You find a dotted node N2, right? And you underline that as well. So in other words, you've now got 2 node numbers that have been underlined. You found a pair. So okay. So now what you're going to do. Those 2 node numbers maybe are an edge. Okay, so then now you go checking in the edge list to see if those 2 node numbers are in the as a pair represent an edge in the edge list. You go checking to see if that pair N1 N2 is in the edge list. Okay, so for each edge, so you now test whether these 2 underlined nodes N1 and N2 are they an edge? Are they in the edge list? Okay, now if that's true, then your undotted node N1 here, well, now you dot it because now you know it's connected, right? Because it's in a connection list. There's a connection between N1 and N2. N2 is already dotted, is that right? Yeah, N2 is already dotted. So therefore N1 needs to be dotted as well, because now you know that N1, node number N1, is connected, because it's connected to N2, and N2 in turn was connected to others, and so on, eventually back to the very first one. You start here. Okay, so you dot N1. So you know it's connected, and then remove those 2 underlines because you're going to loop back again, and then continues from the beginning of stage 2. So you go back to here. Right? Now you find the next undotted node number. Right? We'll call that N1 again, and so on. Right? All right. Now, so say that that pair N1 N2 is not. Let's see what we're doing. The next edge. Okay. Well, then you just check the next edge in the list, right? And if there is no. That's the mathematical symbol. The looks like a capital E mirrored, and then you cross it out so that you're not NOT. You're negating it. So if there are no more edges, these pairs, then comma, I suppose if no more edges, comma, then this is not an edge. Okay. So that's not an edge. Now it's not a disaster. So then what do? Then you move the underline, the marker of some sort that was on N2. Well, you then move it to the next dotted node, okay, and you call that dotted node N2. And then you then go you repeat from stage 3. You go back to here. I've marked it with this asterisk. So you loop back to here and go through it again. Okay. Now, if there are no more undotted nodes, if you've run out of undotted nodes, well, that means you've completed an island. All the nodes in your island have been dotted. They're all, all those nodes are complete. Now, if, as I was saying a bit earlier, if your graph is connected, there is only one island in the whole graph. Okay, so what you now need to do is to check that that's the case. You need to check that every node in your graph is dotted. In other words, every node belongs to your one island, so to speak. Alright, so, okay. So if there are no more undotted nodes, then M it hasn't been able to find any new nodes to dot. So then it moves on to stage 4. Like I was saying, it checks. Stage 4 is just checking that every node is dotted, or in other words, that the graph is in fact connected. In other words, every node in that graph has a path to every other node in the graph. Right? There are no isolated nodes. There's no second island, so to speak. Right. So stage 4, M scans. It goes through the listed nodes and checks they're all dotted. Right? All of them are dotted. Okay, and if it is, it enters the accept state, because now it knows that the graph is connected. Okay, therefore success. So it goes into the accept state, and if otherwise, else, if there's at least one node that is not dotted, well, then it's not that there is no edge from some node to that node, and therefore the graph is not connected, hence fail. Else it goes to the reject state. Okay. Now it's one or the other. So this machine M is a decider by definition. A decider Turing machine does only two things: it either accepts or it rejects. That's it. It never loops. Okay. Looping just means it goes on forever and never accepts nor never. It never accepts and it never rejects. It just goes on and on and on. Turing machine by definition only stops when it, two possibilities, either it accepts or it rejects. But if it does neither of those two, then it just continues processing. It just goes on forever. Okay, that's called looping. Right. Okay, so that's the end of the implementation level description of this machine M. And it's sort of intermediate. You could ask lots of more detailed questions about each of these parts, and then you go right down to the full formal definition. You need to describe all the states, your big Q, all the transition rules, and that's the really tedious part. And I mean tedious, right? There are a lot of details there, and people in practice tend not to do it. And even this intermediate levels, type 2, if you like, intermediate level. It's still an implementation level of description. Even that's not done. This is probably the last time we'll do this, because we're moving on to a new chapter, and we'll be talking from now on just about algorithms, which are high-level descriptions. And but they're sufficient to give you an idea of how a Turing machine works, just by talking about the algorithm. And next session we will get into, in my view, the most fascinating part of theory of computation. Gödel also, but it's not really theory of computation. Gödel tends to be classified as another topic, although obviously related, because the whole history of computation, computers, came out of Foundations of Mathematics. Alright, now, okay, so that's the end of the theory section of Chapter 3, and I promised you in the previous session I would present to you some of the courses, and hence the books, the textbooks, that I will be giving in future years, because I will take you M1, M2 and PhD 1. For the moment I don't have any courses at PhD 2 level. I mean, the whole point of my deGarisMPC is really, it's more geared towards pure mathematics and mathematical physics. One of the main goals is to teach the planet string theory, for example. High level PhD 2 level pure math physics. That's my goal. So all this undergrad stuff that I'm doing now, it's all they're just stepping stones. They're just preliminary courses, prerequisites for the graduate level courses, and M1 are prereqs for M2, and M2 are prereqs for PhD 1, and so on. And most of the courses will be at, in fact, PhD 2 level. I'm still preparing the texts at that level now. When I'm in my free time, not preparing the board or filming or upload or pre-processing and uploading to YouTube. Okay, now I'll talk about I'll just briefly go through some of the courses that I will be giving in future years at the various levels.